at NIT Calicut as assistant professor in mechanical engineering department since August 2019. He's worked at National Institute of Technology, Delhi, in Department of Mechanical Engineering as an assistant professor since in August 2017 to May 2018. He has worked at Center for Solar Energy Technology in Indian Institute of Technology, Jodhpur, Rajasthan as a scientist C, in Indian Institute of Technology, Kanpur, Uttar Pradesh as a senior student research associate. He has published 2 book chapters, 1 book, 7 journal papers, 13 international and 4 conference papers. He has been a reviewer in many reputed journals, which includes Energy Journal of Elsewhere, Scientific Reports, Nature, of Springer Nature, the Energy Journal for the period of 2019 to 18 to 2015 as well, in Journal of Combustion, and in Fuel Journal elsewhere in December 2014. Thank you very much, sir, for accepting our invitation. You can start your session now, sir.
Yeah, thank you very much for your kind introduction for me. And thank you for giving me an opportunity to discuss the very interesting topic on multiphase flows, where CFD is used in a phase change problem. So today we are going to discuss about CFD. So what particular CFD I want to discuss is finite volume method. And we'll be discussing about how the multiphase flows are modeled and solved, for example. And when I'm considering the phase change, I'll be more discussing about droplet evaporation. Okay. So there can be various types of phase changes like boiling, condensation, solidification, melting. So I will not be focusing on solidification, melting, and so forth, but I'll be more focusing on droplet evaporation phenomena, which generally occurs in a sprays kind of scenario, which sprays are mostly used in our IC engines, gas turbines, okay, which are more used in automotive sectors and your defense sectors. Okay, so there I'll be discussing how this droplet evaporation is modeled in the purview of this multiphase flow. So what I'll be doing is I'll be first giving some brief introduction about the multiphase flows, and then I'll talk about how the historical importance of multiphase flow is there and when did it start actually. And then I'll discuss some of the applications of these multiphase flows, and then I'll discuss a very unique feature of this multiphase flows which it has, that is the characteristics of the multiphase flows, how these multiphase flows are different from the single phase flows. And then I will discuss the governing equations. Okay, I will bring out some of the interesting features which are there in deriving these governing equations. These governing equations for multiphase flows. Okay, you must have many cases you must have studied all the derivations for the single phase flow while considering a very infinitesimally small volume and doing derivations for single phase flow. But when it comes to multiphase flow, there is a little they are derived on the same ground, but there is little interesting thing to be noted. So that I'll bring out in this governing equation part. And then I will switch on to finite volume discretization method, which is generally used in any solver. Okay, most of the solvers like ANSYS, ANSYS Fluent, and all others, so they are using finite volume discretization method. So I'll bring out how the finite volume discretization method can be used on a generalized equation, convective diffusion equation. So I will just discuss about some convective diffusion equation and how we can use finite volume for these convective diffusion equations, which are nothing but the model equations of these governing equations. They are same. So once you know how to do with convective diffusion equation, then you can do for any equation same time similar type of discretization. And I will discuss about also the boundary conditions, not only governing equations but also what type of boundary conditions we need to apply in case of multiphase flow. So there are certain differences when we discuss about multiphase flow in terms of boundary condition. So basically in terms of no slip condition, we'll focus, we'll see there are certain differences on multiphase flows in terms of no slip condition. When I'll discuss about this finite volume discretization, then I will also discuss about how to apply boundary condition in a domain. For example, you have this computational domain, then how do you apply the boundary conditions on that? When you discretize a domain, then how do you apply the boundary conditions? So I will just show how the finite volume strategy is used in general to solve these governing equations. And then I will just give a one algorithm which is famous algorithm, that is called a simple algorithm to solve the equations. Okay, Navier-Stokes equations. So basically these will be Navier-Stokes equations. So a simple strategy will be discussed, and that can be commonly with little this discretization with little modification and little incorporation of two terms for the multiphase flows. It can be straightforwardly applied and solve the problem can be solved. Okay, once I discuss this thing, I will discuss about the, as I said, the phase change thing. So I will just discuss about the spray evaporation scenario, how the spray evaporation scenario is there, and how this spray evaporation modeling is done. So basically, they in the state of the art, the modeling is a single droplet modeling, and when you model the single droplet evaporation, it is assumed that all other droplets, they are also following the same behavior, and or on every droplet these evaporation models are used, so that we can predict the evaporation rate of these droplets, so that once you get a mixture here, it will have a burning of the fuel and air, and we'll get a combustion here. Okay, in any internal combustion engine devices or gas turbine devices. Now, once we discuss this, there is a elegant theory and the modeling strategies for single droplet evaporation, which makes one model different than the another model. And I will just show you how the different models are used for single droplet evaporation. And I will just again show you how the governing equations of spray evaporation model. So I'll just revisit the same these governing equations, and how these governing equations for spray evaporations are modeled in terms of the source terms being incorporated for spray evaporation. Okay, so that with the passage of time I will discuss about that, and where the spray evaporation terms comes in. So once we get to get the governing equations, then I will just show you how the ANSYS Fluent is solving a spray evaporation problem. So for that, in order to focus more on spray evaporation and not to consider many other effects, I just will show you some 1D case for spray evaporation and how it is used, and how the spray evaporation models are compared. And I will just finally give my some concluding remarks on the subject. Okay, so first thing first is, what are multiphase flows? Okay, so multiphase flows are generally nothing but it has a two or more than two distinguishable states or phases. Okay, so states or phases means either it will have a solid, liquid, gaseous phase. So one can have a solid phase, another can have the liquid phase, like that. One can have a liquid phase and another can have gas phase. Okay, but also it for example, like air bubbles in water or suspended solid particles in air. these are some of the examples where you can see two distinguishable states or phases. Okay, so one is a solid phase, another is a, so you can distinguish them easily. So such a scenarios can be called as multi-phase flows. Okay, so in other cases also, it may happen that there may be two distinguishable phases, but it will have a different chemical property, distinguishable phases in terms of distinguishable chemical properties. For example, oil in water. So oil chemically it is different, water it is chemically different, but both are liquid in liquid. So such a scenarios are also comes under the purview of multi-phase flow. So when there are two phases in picture, like say solid phase and gaseous phase, then we say that these are two phase flows. If there are three phases involved, then we call it as three phase flows, and similarly more than two and three is generally called as multi-phase flows. Okay, now these multi-phase flows are mostly seen in two types of scenarios. Okay, one scenario you can see is that the fluid one, this whole fluid one can be separated by the whole fluid 2 with a distinguishable interface. This is called as interface. Okay, so there are two continuous phases. One is continuous phase, another is also continuous phase. There is another scenario which is called a dispersed flow. The previous one is called a separated flow, where fluid 1 is completely separated by the fluid 2 with the sharp interface. They are not there is no mix, there is no voids, and this thing, there are no voids in the fluid 2 or either in fluid 1. They are continuous, but they are distinguished with respect by the interface. Second is a dispersed phase. In a dispersed phase, the second phase, so this is a fluid 1 and the other one is fluid 2. So you see the fluid 2, this is also fluid 2, fluid 2, fluid 2. So fluid 2 is dispersed. It is not a continuous. It is somewhere here, some part here, some part here, some part here, like that. So you may have uh, in the continuous domain, you may have the second phase. This is a primary phase, and the second one is called as secondary phase. So secondary phase is not a continuous, it is a dispersed in the continuous domain. So such a flow scenarios are called as dispersed flows. Okay, so having seen two types of scenarios, I'll just look at the historical perspective. Okay, so in the history, if you'll see and if you'll study the fluid mechanics, many of the fluid mechanics research has been done on mostly single phase. Okay, single phase flow. And the beginning of the study of the multi-phase flow starts with the World War II. And there initially the people have started with working with homogeneous mixed model, where the main problem is to find out the viscosity. In homogeneous mixtures, what they do is they essentially consider a one equation for the both the phases, and suppose there are certain properties to be included. For example, you have this equation del phi del t plus, say I'll just write it in 1D, del phi del x, and you have certain properties here like mu by rho, uh, and you have del 2 phi del x2. In that case, these properties will be mixture properties. Okay, so what here the problem then becomes to find out what is the viscosity. So main problem in such homogeneous mixed models is to find out what is the mixture viscosities or mixture properties. Okay, for example, if you have a heat transfer equation, then you might have instead of viscosity, you might have thermal conductivity. So in that case, the main problem will be to find out the thermal conductivity of that model. Most other type of models were based on separated flow models. Okay, so in separated flow models, the basic initial beginning started with this Lockhart Martinelli. Okay, this Lockhart Martinelli, they essentially postulated that, say for example, you know the pressure gradient. Suppose this is the phase one and this is the second phase. If you know the pressure gradient in the first phase, and if you know the pressure gradient in the second phase, and somehow this relationship between this the pressure gradient in phase 1 and pressure gradient in phase 2 is known, then we can calculate the total pressure gradient. Okay, but the problem in this is the total pressure loss is not a linear function of, there is no linear relationship available between delta P1 and delta P2, and that is the problem. This non-linear relationship between delta P1 and delta P2 made them to do lot of derive lot of experimental correlations. Okay, so they essentially gave lot of correlations for different scenarios, so for the specific cases. Okay, so based on the case to case, they gave different correlations, and their correlations found to be very good. And but the requirement was the different models has to be used. Okay, so the situation when the different regimes are applicable, which lead to the concept of flow regime map. So what happens is that is this particular practice, then people started following, and they started making flow regime maps, because a certain flow regime will have a certain flow model correlation, another flow regime will have another correlation model. So people started making some correlation maps like that. If you see the books on that, you will get to know there will be some the dilute phase flow, and uh, so things like that. So there will be different in the same phases, there will be different regimes evolved in time. So or in particular instant. So for that particular scenario, there can be different correlations. So people started making what are the flow regimes. Okay, and in that flow regimes, what are the Lockhart Martinelli relationships, and based on the flow regimes, the people used to start this experimental correlations and used to get results. Now that uh, people started more on flow regime maps. So Teitel and Duckler also suggested a map which is experimentally found on 5 non-dimensional groups. Okay, and this model again found not to be universal. That is a problem with this correlations. Okay, these correlations uh, are very good for different maps, but they are not universal. They found to be limited to only certain cases where you have a liquid and gas flows, and for instance like microgravity. Such situations, they are limited and they are not found to be universal. So what is the way forward then? Is that the most of the perspective for solving such a problem is to go for a numerical simulations. Okay, so various scenarios which we observe in as I said, one is a separated flow kind of case, another is a dispersed phase flow case. Okay, so in this I'll not talk this separated flow models. This okay, this basically you can also solve using volume of fluid method or any other method. But let us focus more on this dispersed phase type of scenarios, where we'll see that our droplets evaporation and kind of scenario is present. So in these cases, you have your main phase, you have a primary phase, that is primary phase, and primary phase is seen to be a continuous phase. Okay, which is a continuous case. And the secondary phase, it is a dilute case. It is not a continuous, it is a discrete phase. Okay, now based on the amount of their presence, they can be classified as dilute or dense. Okay, so if their density is very high, they are closely packed and many drops are there, and highly packed are there, then we say that they are dense. And if there's distances between the two droplets is very high, they are discrete and separated by large distances, then and they are very less in numbers, essentially the number density of number of droplets per unit volume is very small, then we say that. So number density is, number density means number of droplets per unit volume is very small, number density is small, then we say that it is a dilute. And if the number density is very high, then it is called as the dense flow. Now what are the properties with dense flow and discrete dense flow and dilute flow? Now when the dilute flow is there, since their separation between the two is very high, it is unlikely that they will come in contact with each other in the future times. Okay, so there will not be, it will not happen that this droplet and this droplet will collide with each other and form a group, or maybe form a big size of droplet. So such a kind of interactions will be very less in case of dilute cases. And in case of dense cases, it may happen that they may interact, because since the droplets are very close to that, they may interact with each other. So there may be having a strong collision, strong interaction between themselves, not only between themselves but also their interaction with the primary phase, okay. Now in case of dilute phase, there is an interaction between the dilute phase, secondary phase and primary phase. But since the density in case of a dense flow, number density is very high, the amount of interaction as compared to the dilute flow will be very high, okay, in this dispersed phase scenario. Okay, now these scenarios can be seen in your horizontal pipes, in vertical pipes like bubbly flow, slug flow. These are the flow regimes which I have just discussed just in the previous slides. These are the various flow regimes. For these flow regimes, people use various correlations. If they want to solve annular flow, they have Lockhart-Martini correlations, use those correlations, get pressure loss and the other variables of interest. Similarly, for horizontal pipes, in the horizontal pipe we have in the same pipe we have various single phase liquid, bubbly phase flow, plug flow, different scenario at different x locations. Okay, so for this particular scenario, these correlations are not seen to be universal, and they need to be modeled using CFD. So when you go for a CFD, what do we do is, whenever, suppose this is our domain, so this is our domain, for example. So I'll just make a small introduction. Now suppose this is a domain. So in essentially the partial differential equations, they are valid for full domain. Okay, so in this domain the PDs will be continuous, and they will be under the assumptions of continuum mechanics, they all the PDs will be continuous. So suppose, for example, this is a solution variable, then that solution variable will give you continuous solution, that is xyz, and maybe in also time. Okay, now when you do CFD, then this phi will be essentially not all x location, but it is a function of uh, delta x, delta y, and delta g and delta t. Okay, what does it mean? That it gives you solution at these discrete locations. So you will get solutions at discrete locations. Okay, so for that, to get the discrete location, this continuous domain is converted into very small domains. So this is a one domain, this is another domain, this is another domain, this is another domain. Okay, the process of converting a large domain into very small domain is called as grid generation. You must have heard this, grid generation. So grid generation is an essential part of CFD, where we convert any continuous domain or full domain into discrete domains, and over these discrete regions, which are small regions, we get the solution. So this phi is a solution at this delta x, delta y, delta g. Phi is a solution at another delta x, delta y, delta g. Like that, we get discrete solutions. Okay. Now, for a continuous phase, there are two ways of doing. Now, for a continuous phase domain, you can generate a grid. Also, for a secondary phase, also you can generate a grid. Okay, and if you use a grid for continuous flow, if you use grid for primary phase as well as secondary phase, these kind of problems are called as using solved using Eulerian model. Okay, Eulerian model. These are called as Eulerian model. So one grid for the continuous phase, another grid for the discrete phase is considered, then Eulerian model. In second case, there is a scenario called as Eulerian Lagrangian. So in Eulerian Lagrangian, what is done is that for a continuous phase, you will have a grid. But for a discrete phase, you do not have a grid, and we just track the position of this particle by using your equations like dx, position dx by dt, which is nothing but your velocity. So using this equation, you can track the positions of the particle, you can find out the velocities of particle using Newton's second law of motion and get the solution. But for a continuous phase, I mean primary phase, we will have a one grid. Okay, so these two scenarios are there. First one is called as Eulerian, and second is Eulerian Lagrangian. In Eulerian, primary phase is also considered as Eulerian, secondary phase is also considered Eulerian. In Eulerian Lagrangian, primary phase is considered as Eulerian, and secondary phase is considered as Lagrangian model. Okay, now when there is a dilute kind of scenario, okay, now when there is a dilute kind of scenario, then in that case, this Eulerian Lagrangian model is very good. But when it comes to dense kind of simulation, then your Eulerian model seems to be very good. In the sense, why? Because in Eulerian case, if there are more drops, now these discrete phases actually more closer to us continuous kind of. Okay, this scenario you can say more close to continuous than the dilute case. Okay, so per grid you have many particles. So in a particular grid you will have a sufficient particles, and you can assume that a certain continuum is exists in case of dense flow, and then Eulerian model will not fail in such scenario. So that is the reason Eulerian model is very this thing used in dense flow. In dilute flows, Eulerian Lagrangian model used, because this Lagrangian model what it does is it solves for every this page. Suppose this is 1, 2, 3, 4 and 5 dispersed drops are there, then this Lagrangian equations will have 5 equations. Suppose this number of drops increases, you see, suppose it becomes very dense flow, then number of drops per volume will increase. And essentially in a Lagrangian case, you will have to solve many equations, and that will be very computationally costlier. So Eulerian Lagrangian models are more favored for dilute cases. Okay. However, present day scenario, with having a very good computers, you can even go for Eulerian Lagrangian model. And for the Eulerian Lagrangian model, the best, present day people preferring Eulerian Lagrangian model, because in case of, suppose you model this secondary phase using Eulerian model, then you get something called as numerical dissipation, numerical dispersion. Okay, numerical dispersion and dissipation. This is inbuilt in our scheme, inbuilt in our scheme. Okay, so whenever you have these equations of this type, del phi del t plus u, this is a way, this looks like a convection, right? So if you have these equations, then you may have some gamma here and del 2 phi and del x square. Now in these cases, in order to get this convection, you essentially use some sort of upwind schemes or backward schemes or forward difference scheme. By using those schemes, you essentially adding some more term here that is called a numerical dissipation term or things like that. So these essentially brought in the numerical dissipation inbuilt in that, and that creates some problem in getting the correct solution. Okay, so Lagrangian models do not have this kind of numerical dispersion and dissipation problem. So these Eulerian Lagrangian models are nowadays also seems to be found this thing. Okay, and the various introduction, I mean there are various books to give you essential introduction, whatever I was talking about, Lockhart, Martellini, this kind of models you can find out in this very good book, Two Phase Flows by Wallis. It will discuss about one-dimensional flows, but in essentially the flows are not one-dimensional. Many times they are 2D and 3D in practical situations which are considered in aerospace industries and defense industries. So these models or the whatever the theory given here may be just restricted to your 1D simulations or just academic purpose. Some other textbooks like by the Croway gives you very good introduction to the modeling around about the Eulerian Lagrangian model. Two phase flow model book is a very good book by Ishii and Hibiki, which shows you how to get the governing equations for the continuous phase as well as the secondary phase, discrete phase, in the scenario of the dilute phase as well as dense phase. So this is a very good book, and the modeling of this is essentially a research of the present days scenario. It's very tough job to model the to multi-phase flow, and this book shows a very good introduction to modeling. Those who wanted in further, I mean after the lecture want to pursue, they can go through this very good book. There is another good book by Aeon and two, which discuss about the computational techniques for multi-phase flow. So what are the techniques which I'll be, they essentially the finite volume method formulations we follow is consistent, but it doesn't use the same terminology which we are using, but those who want to pursue, they can see these books for the modeling of the equations as well as some of the CFD stuff for the multi-phase flow. Okay, so this is just for your this thing, but I'll also discuss now the applications of this multi-phase flow. So these multi-phase flows are found in the various scenarios, not only in industries and these things. They are ubiquitous in nature. So for example, this rainwater falling on the ground. Okay, so the dust, sand dust that is there in the atmosphere, that is also can be modeled, I mean, as a multi-phase flow. There are certain applications where spray drying and other things are used. So this hot spray is, this is sprayed, and drying gases are out and the product is taken out by using this So this also this drying uh, applications. You can model, I mean, there's a model as multiphase flows. You have this coating. Okay, so spray coating is also one example where the spray evaporation, spray vaporization, and multiphase flow comes into picture, and you can model these flows using the content given in this lecture. Substrate formation, or I mean lamine, that is also one application from the manufacturing side. Another application from manufacturing side is the spray cutting. Okay, so water spray cutting, this is also one example. Then you have this you have this flow systems. So you want to transfer material one from this location to this second location. In that case, these multiphase flows are used to transport essentially some these particles from one location to another location. This is also one application. One another application mostly you seen in your restaurants or malls, these sprinklers, water sprinkler systems are installed, and these water sprinkler systems you use spray in order to extinguish the fire which may potentially come there, and which may harm the focus of our interest is a scenario which happens in a gas turbine kind of case. So in a gas turbine cases, you have a nozzle spray where your the fluid or your fuel is injected, and when that fuel is injected, there are many things happens. Okay, so cavitation, exit flow, and then that once that thing happens, then there may be the primary breakup or secondary breakup of the layers may be taken, or droplets may be isolated, and this thing, and finally they will form spherical droplets or non-spherical droplets also. Most of the time they will be spherical based on the flow conditions. So once the drop has formed, what is the necessary condition for the combustion is that this drop should essentially vaporize. Okay, so if the vaporization of this drop is very very important to model. Okay, if there is a lag in the vaporization, suppose these drops are formed and now they are taking they are also moving, these drops also moving, and if they are taking a lot of time to vaporize, so what will happen is that they will take lot of space in order to finally, so instead of having vaporized here, they will get vaporized in another location. Suppose this is the length of the combustor, for example. Suppose this is the length of the combustor, then in that case it will take larger distance to get completely vaporized if this vaporization time of the droplets is not proper. So if your model here, then it will start combustion, and the now the efficiency of this combustion depends upon how how efficiently these vapors vapors are formed, and also the design of the length or the design of the cylinder. For example, length of the cylinder depends upon the vaporization rate. So if there is a delayed vaporization, if the models are not correct, and they could not predict properly, then you might land up in designing a wrong combustor or long combustor, and designing long combustor will be bulky and of no use. So modeling of this vaporization in a numerical scenario is a very very important task, and that is what our focus will be, to show you how we can model vaporization in the in this multi-phase flow scenario for the applications of this aerospace industries or automobiles or stationary power plants, gas turbine based power plant. So before going to the derivation of the multi-phase flow equations, let me talk about what are the characteristics of these multi-phase flows, how these multi-phase flows are different than the single phase flow. So what difference you see in this multi-phase flow, as we have also seen. So in cases we had this domain and we had this a droplet, for example. So we see that these droplets may at another time they may change their shape. Okay, so what is this particular region which I have shown? This is a droplet, but essentially for this page and this page, this particular region is an interface. This interface is keep on changing. Okay, so there is a existence of the interface. First thing is existence. It exists in all cases, in all multiphase flows. The interface is existing, and not only that, this interface is dynamically changing. Dynamically changing means changing with time. So it keep on changing. Its shape may be there, and at other time it may be different. So it's how do you model such thing? It's very complicated. So such a characteristic it has. What other thing is, it has a significant discontinuities in the flow properties. So here, for this, for example, the flow property of this, suppose this is air, the property of the air, say density of the air is very different, and this density of this phase, for example, this is a water, then we know that density is very large in case of water as compared to air. So these large discontinuities, they happen. So you see, there is here the large, then again there is a large, but in between there is a small. So this kind of discontinuities in fluid properties you can see in all multiphase flows. What is another thing is, this scenario around this, for example, this particular phase. So near this particular interfaces, many things happens. Many complicated flow field scenario come into the picture here. Near this, very near to this, so you may have formation of boundary layer, thermal boundary layer, and velocity boundary layer, and many complicated flow scenario may come. You may have the surface tension acting on that, and things like that. So complicated flow fields are there in near the interfaces, and modeling that is again can be a challenge. Okay, say for example, we are right now talking about irrespective of the flow type, laminar or turbulent. Now suppose in case you go into the turbulent flow, now once the turbulent flow is there, now in continuous flow you may have eddies. So now these eddies may interact with the discrete phases. Now this interaction of these eddies with this dispersed phases is a complicated scenario. Okay, so you can see this are mingling with the droplets and at any other times. And what other characteristic it has is, irrespective of in both the phases or both the flow scenarios, it can happen that this phase interact with other phase, also other phase is interacting with the first phase. Okay, this secondary phase is interacting, primary phase is interacting with secondary phase, and secondary phase is interacting with primary phase. And what is happening also is that, if there is another drop, then this secondary phase is interacting among themselves. Okay, so such a kind of interaction you can see between the phases. And also what is another thing is multi-scale. Okay, what does in multi-scale means? You may see very small droplets, you may see very large droplets. Okay, also things which are happening here, they may be over the time, they may be they may be happening at very short time. Some things are happening at large, it takes large time to happen. Okay, so you see in terms of space, in terms of time, you see there are scales, multiple time scales and space scales. Okay, so these are varying, and you see multi-scale nature of the problem. So you have a so in short, you have dynamically changing interface and discontinuous of the fluid properties, complicated flow fields, interaction of eddies, exchange between flows, and multi-case. Now, due to the scaling nature of the lab scale model, for example, you have the multiphase flow scenario, and you want to do experiments. So suppose you want to do experiments on multiphase flow. Now when you have a big system, for example, you have this big system. When you do experiment, we try to use a scale model. Okay, now in the scale scenario, it is very difficult to do lab scenario. In these cases, maybe you have a droplets of size d1, but what it'll do when in this experiment, the droplets may be in the same d1. Okay, so it is not scaling down. So scaling down of the big model, big this actual devices into models is a problem, lab scale model. So in a future, for the real time problems which are occurred in aerospace industries and defense sectors, what is best scenario is that what one can look at is that to have a good validated and verified CFD models. Okay, validated and verified, that is very important, because CFD is a, to note, CFD is a approximation method to solve the PDs. So we need a validated and verified model. Uh, and now for this current scenario, because of these limitations of lab scale models, it seems attractive to go for the computational fluid dynamics softwares. And present day scenario is such that we have very good computers, high speed computers, which can handle this multi-scale natures. It can handle turbulent flow natures. It can handle some sort of complicated flows and discontinuities, and fulfill this complicated characteristics of multiphase flow. So we need see the importance of CFD in that. But to do CFD, we need a governing equations. Okay, so we need a governing equations like Navier-Stokes equation type of equations for multiphase flow. And what I'm trying to show here, in general, the derivation of the governing equation for multiflows is complicated. I will just show you in short next how they are done. Okay, now we have this scenario. We have one phase, and we have another phase, primary phase and secondary phase. Now secondary phase is a discrete phase. Okay, but to model, we can model this as continuous. There is no problem. Okay, but what about this? So this is also assumed that this also will be modeled as a continuum. Okay, so this is also modeled as a continuum. Now, and this need to be modeled as a continuous phase because it is a discrete in nature, and it discrete in nature, then how we'll solve it. So we are starting with some this thing that we assume that they are also continuum, and they are intermingling with each other and interacting as a continuous phase. Okay, so it is assumed that this dispersed phase so is a continuum, and they are intermingling with each other, and they behave as if they are continuous phases, not discrete phases. So with that case, we can derive the Eulerian kind of two-phase flow equations, one for the first phase and another for the, governing equations PDs for the continuum phase, and that is what we wanted to show here. Now, when you do this assumption, continuum assumption, and when you see the discrete nature and you wanted to put it in a continuum framework, what we do is that we say that we now discuss about the averaging properties rather than the individual properties. Okay, so to characterize the discrete phase properties, an averaging procedure is done. Okay, this averaging procedure is similar to what we do in turbulent flows. Okay, but right now we are not considering any laminar or turbulent flows. So even this flow is not turbulent because of this nature of the discrete nature of these particles or droplets. We need to put them into continuum assumption. We are discussing about the averaging procedures. Now there are different types of averaging methods. One is a time averaging, one other called a space averaging, and ensemble averaging. time averaging, we take data at different times, and then we average it by total time, that we get the time average value of that. In volume average, we volume average on we average on the length of the domain. And in case of ensemble average, which is most likely used, is these are different realizations. Okay, so in first realization, we note down the values. In second realization, we note down the values. So these are like number of experiments. So this is experiment number 1, experiment number 2, experiment 3, and then we average these values. Okay, so this is called as ensemble average, and these averages are most widely used. So you can have essentially 3 varieties of averaging. So if you do averaging of this discrete nature of the particles to bring them into continuum assumptions, their now averaging properties are not local properties. Averaging properties are their global properties. Okay, but if you want local properties, this local nature of the droplets is lost. Okay, now to bring in those local nature, whatever the loss is there in the local nature. Okay, local nature is lost. So to bring in that loss into picture, there you need a semi empirical closure relationships. Okay, so if you put in these closure relationships, which are semi empirical in nature, experimentally found, or things like that, then these semi empirical correlations close the loss information due to averaging and fulfill our objective. Okay, so that is the procedure. Okay, now these derivations. So in case of single phase flow, what do we do is we take some infinitesimally small volume. Okay, and we also take maybe another case like we take control volume. So there are 2 scenarios in which we take in single phase flow. Similarly, in also the multi-phase flow, we derive the local instantaneous conservation equations for the phases. So for phase 1, we will derive using this same concept for phase 1 and phase 2, or maybe using this control volume concept for phase 1 and phase 2, we can derive the equations. Okay, so once you get the local equations, now you see this is very similar to our single phase equation del rho. This is a continuity equation. Okay, conservation of mass, incorporating conservation of mass, del rho by del t, del dot rho u. Now this k represent the phase. So if there are 2 phases, it will be k is equal to 1 or k is equal to 2. So it is a local equation, local continuous instantaneous equation. Now to get the average equation, essentially you have to introduce something called as phase indicator function. Phase indicator function is chi, phase 1, phase 2, phase 3, like that. This k will vary. If this chi is 1, if the k phase is present in that time. If it is not present, if k is not present, then it is 0. So its value is 1 or 0. If it is present, then its value is 1. If this value, if it is not present, then k1 phase, chi1 phase is not present, then it is 0. Chi2 phase is not present, then its value is 0. So this is the property of this phase indicator function. Once you take this phase indicator function and multiply this equation by this phase indicator function and take the average, so any type of average, so say ensemble average you have taken, then once you take the averaging, you get these additional terms. These additional terms are observed. These are called as interfacial source terms for mass. Now since this is a continuity of mass equation, mass conservation equation, so whatever the source terms we got, these are called as interfacial. These are obtained because of the whatever is happening at these interfaces. Okay, whatever is happening at these interfaces, they appear as a source term in the in the continuity equation. Okay. Similarly, you can derive the momentum equation. So you derive the momentum equation and you get these terms uh, as a source term for momentum. Similarly, you can have an energy equation and you will get source terms for the energy. Okay. Now, once you get this equations in terms of averages, now see there are certain things where you see the averages of the product. Suppose this is a one quantity, this is another quantity, and then there is an average of these two quantities. So calculation of these products of I mean averages of the product is very difficult than calculating the product of the averages. If there is, this is a first quantity and this is a second quantity, then this is very easy. This is very easy as compared to calculating such a quantities. So we need to do some sort of procedure here in order to separate the mean flow from the fluctuating quantities. And this is similar to what we do in a turbulent flow. We take the and average, this is mean, and any quantity. In that case, we used to take any quantity is high, that is the mean, and used to take fluctuating quantity. Okay. So like that. Now in this case it is average, so you have to take average quantities and the fluctuations. Okay. So if you do this and if you drop these bars and brackets and parentheses, you get finally these equations. Now these equations are very likely you can understand that, and the sky is now replaced by the alpha, and you get the this is a continuity equation, this is a momentum equation, and this is a energy equation. So these are very similar to what we generally see, with only difference in source terms. So this is a source term, this is another source term, and this is the here another source terms for the particular mass, momentum, and energy, which is happening at the interfaces. Because of that interfacial exchanges and what are the complicated processes happening over the interfaces due to nature of the characteristics of, or due to nature or characteristics of the interface. Okay. So if we know these terms, then we need some equation for this to solve. So if you use a linear relationship, this type of linear relationship, then your equations becomes another easy. So this is kth phase from to lth phase to l to k phase, like this interaction is there. So these equations becomes very easy, and then you can solve this with this known linear source terms for mass, linear source term for momentum, linear source term for energy, and you can solve these equations. Okay. Now these equations, what are the equations I have showed you? These equations are for both the phases, phase 1 and phase 2. Now there can be another models where we can say that instead of having two different phases, 1 and 2, they are the same phase. So we say that this is a mixture. Let us say that there is a mixture of this phase, and instead of solving two separate equation for one phase, we get one set of mass and momentum and energy, and two for mass, momentum, energy in case of previous models. In these models we used to get for first phase mass, momentum, and energy equation. Similarly, mass continuity of mass, momentum equation, and energy equation for second phase. Now there is another scenario which is called a mixture model, where we do not consider two separate sets of equations for two phases or more than two phases, but what we say that they are the mixture, both the phases having a mixture, and then we solve the equation for the mixtures. Okay. So like this you can solve for the mixture phase. M denotes mixture. So this is a mixture continuity equation, this is a mixture momentum equation, this is a equation for energy for the mixture, and here the mixture velocity the mixture density, mixture viscosity, mixture thermal conductivity, mixture velocity, mixture energy. These are defined as a sum of products of alpha k, rho k. In case of rho, in case of mu, it is alpha k, rho k. So you have to sum product of all the phases. So alpha 1, mu 1 plus alpha 2, alpha 2, mu 2, and based on that. So this will give you the mixture viscosity. Similarly, thermal conductivity, similarly, mixture velocity. So uh, you can solve this for mixture and get the properties, and you can also get the individual phase velocities. Suppose you get the mixture velocity from this, then you can calculate this the individual phase velocities, uh, and like that. So this is another model. The third model, which is used in Eulerian Lagrangian approach. So the derivation which is shown previously, that for the first phase you may have mass, you may have momentum, and you have energy equation as shown in other cases. But in this case, the Lagrangian model, that secondary phase is doesn't consider any grid, and just we track the droplets. So we just trajectories of the particulates are calculated, and we solve this momentum equation. So this is Newton's second law of motion: force is equal to mass into acceleration. So this is the total derivative, and so we have just different differential equations. We solve this differential equation in order to get the velocity of the droplet, for example v instantaneous of the droplet. And we another solve the mass of the droplet. What is the mass of the droplet with source term, and what is the temperature of the particle or droplet. So we solve these equations along with the mass, momentum, energy equations we derived previously. For second cases, we know the velocities. We point out the mass of the particle, temperature of the particle, needed properties, and also we can track that by using your distance function dt by dt, by knowing. So we can track the location of the is droplet by knowing their velocity. We can find their position, and so this Lagrangian model has these equations to be solved along with that. That is the point to be noted. Okay, now what are the boundary conditions generally come in this cases? So what happens is that so say most of the cases we may have these kind of scenarios. Okay, I'm not talking about symmetry and periodic cases. That also can be handled by knowing the Neumann or Dirichlet type of boundary condition. They can similarly be handled like that. But let us say this is a wall 1 and wall 2 scenario, and you have the inlet and you have the outlet scenario. Now in inlet cases, suppose you have a mixture model. So if you have if you are having a mixture model, then at inlet your mixture velocity will be whatever the given velocity in the at the inlet. Okay, similarly, now this is a u is a x component of the velocity, so y component of the velocity vm will be, and other component, third component, if it is a that will be 0. That is what it is meant. Suppose it is Eulerian kind of model, then in that cases, instead of mixture properties, you have to give what is a alpha 1. Suppose there are two phases, what is alpha 2? So that value will be given. So Dirichlet condition means, in Dirichlet you have this given value. This is always given. Known value. This is always given. Okay. So you have to specify what is alpha 1, alpha 2. You have to specify what is u1 and u2 at the inlet. And v1 and w1, v2, w2 will be 0, like that. So these are Dirichlet conditions with given values. Dirichlet conditions means always you have any function will be a given function here. Okay. So that is Dirichlet. A Neumann condition at any function will be given as a derivative. Okay, this is a Neumann condition. So at outlet, generally a Neumann condition used, and for mixtures you can use Neumann conditions like U. This is should be V and this should be W. So U, V, W, they should be 0. So they considered to be 0. Here, what is meaning of that? What is the meaning of that? It means that at the outlet it is considered fully developed. Okay, it is this is assumption so made while deriving this. It is assumed that they are fully developed. For the Eulerian kind of scenario, alpha. So alpha will come into picture. U, V, and W, they all has to be 0. So the derivative of alpha, U, V, W is 0. That is called a Neumann boundary condition. And at solid boundaries, now at this solid boundaries for mixture model, so in case of mixture model, UM will be 0, VM will be 0, and WM will be 0. This is called a no slip condition. At this thing, you have a no slip condition. Okay. And in case of the other flow, when you do not have a mixture model, if you have one phase and second phase, then for a continuous phase, you use a no slip Dirichlet condition. Okay, point to be noted. But for alpha, for continuous phase, we use Neumann condition. And for the secondary phase, we use slip conditions. Whatever value of UD is there, whatever the value of wall is there, if any motion, so that UD wall has to be specified, VD wall has to be specified, and WD wall has to be specified for dispersed phase. So this is for dispersed phase, this is very important to note. For a dispersed phase, you do not have no slip condition. You always use slip condition. There is always slip condition. Otherwise, if you give no slip condition, the droplets will not be moving, droplets will not be interacting, droplets will not be bouncing back. Okay, so that slip condition is mandatory. And what about alpha? Alpha D, once you know alpha C, alpha D is already known. So 1 minus alpha C is a boundary condition at the wall. So these are the boundary conditions generally used. And how do we do finite volume discretization, that I will talk. So this is a generalized convective diffusion equation. So this is a these two terms are convection term. This is a diffusion term. This is a transient term. Okay, and this is the special convection, and this is a diffusion term. So this is generally a convection diffusion equation. This is similar to what we have seen. Now phi can be represented by alpha rho like that. So phi in first case you can replace phi by rho, rho u like that, and can be k, and you get the similar type of equations. Okay, so similar nature of equations. So let us discuss the finite volume method for such a problems. So when you have this governing equation, so this is your, for example, this is a governing equation of this form: del phi by del t, del dot u phi is equals to alpha del dot del gradient of phi. Then in that case, in CFD, first thing first to do is integrate. These equations are volume integrated. So you see, we have volume integrated here. So this term also need to be volume integrated. Okay. So this term is also volume integrated. This term is also volume integrated. Now we want to convert this volume integral terms into the space integral term. Okay, control space. So there is a theorem called Gauss divergence theorem, which is shown like this. So we use that property and convert this volume integral into surface integral. We convert this volume into surface integral, we get these equations. Okay, and since this integral can be taken inside because this properties are del phi has no effect, del t is constant, it's not moving with time. I mean the reference frame is fixed. So in that cases, this can be taken inside, and we can write this equation in this form, n equals to 0. Okay, so this is first is a transient term, and this is a convective term, and this is a diffusion term. So let us see how we do finite volume discretization of this term. So now these are integral equations. Okay, so in CFD finite volume method, we always solve integral equations, not these equations. We convert these equations into integral equations. That is the point to be remembered. And these integral equations are then solved. So for the first term, for example, this first term, so this particular integral, this particular integral over this particular cell, for example, for this particular cell is nothing but the average of phi. Volume integral of phi dv is nothing but the average of that phi, and represented as the phi p value is the average value over this whole domain, this is a cell, one cell. So phi p delta v, this is a volume. Okay, delta volume. So phi p delta volume, this can be converted as, this can be written as phi p del v. So in finally del t, this can be represented as Euler forward in time. So n plus 1 minus n, you can write delta phi is already there. Phi p, now this phi p is discretized with respect to time. So phi p n plus 1 is new time. This is a new time, and this is a old time. Okay, that is a convention we use for moving from one time. So we have to move from time 0 to time 1 2 3 like that. So in that case, this n is 0, and n plus 1, n means the old one, n plus 1 means new, like that. So new minus the old one divided by delta t. This way you can discretize the first term. For the second term, which is nothing but now the surface integral phi u dot ds. So we have to take a surface integral at all the surfaces. So say for example, you are looking at this face. We have this one face, we have this one face, we have this another face, we have this another face. So we have 4 faces. For example, in 2D cases. In 3D cases, we will have more than that. So for say for example, you are taking integral at this. So surface integral of phi u dot ds is at those surfaces, at E surface, at W surface, at N surface, at S surface. So you can write them individually like this, and we know that delta S in case of E is nothing but delta y1. Okay, so here you see this is nothing but delta y. This distance is delta y, and we need to get the area of that. So what do we assume? In 2D cases, we assume that the third direction is always unit. So delta y multiplied by 1 will be the surface area, and the sign of the surface area, since we have the in the flow direction, your normal is in flow direction. In this case, the normal is in the reverse direction. So we can see those changes by the notation. So delta y into 1 I cap, delta y into 1 minus I cap gives the area at east face, that is the front face, and the west face. This is the east face, and this is the west face. So areas are surface area oriented in negative direction. This is oriented in positive direction. That is what. And in north and south also, you can take like that to get the north and south. For north case, we have this length. This length is delta x, and another length that is nothing but unit. So in 2D cases, always consider as unit. So area vectors are like that, and when you substitute them, you can get these equations. Okay, so these equations you can get. So you have already integrated them. So phi u integrated is nothing but phi u, average phi u at that E point. At now at this phase, whatever the average, total average on this, I mean average on this phase is calculated at this point E. So that phi u E and that surface area vector phi u w, similarly phi u w like that, and you get this equation. Okay, now we represent these equations like this. So phi and u E surface area, that is written as F. So UE delta y Fe, UW delta y is written as FW, Vn delta x represented by Fn, and similarly. So phi E, phi W, phi N, phi S. You remember this phi is what? Phi is our this phi. Okay, and this is another variable. This is called as convective variable. Okay, this is your flow variable, and this is your convective variable. Okay, this indicates what is the flow direction in which that your del phi del x is going. So suppose you have u del phi del x, it shows what is in this del phi del x is in which this direction, u direction. So you have to identify these variables. So those variables goes in Fe. Okay, and phi variable remains there. So there are, in order to discretize these terms, phi, phi w and Fe terms, we use this method. So for example, to calculate this ue, uw, un, phi n. Now to calculate this ue, u phi, uw like that, many cases this central p values, u and central east, these values must be known, may be known. Okay, and from this interior points or cell centers, we need to find the values at the faces. So what do we do? We take the average of this and we get the value at E. We take the average of P and E and we get the, so you see UE is calculated by taking whatever the value at pth point and whatever the value as cell center UE, and take the average of that, get the UE. Similarly, to get the average at UW, for UW, you take pith cell and UW at the the back of that. Okay, so PW. So this is a capital W, as I shown in the figure. Here I have shown capital W. So P at what are the velocity at P, what are the velocity at W, that average will give you at small w. Similarly, V velocity, here only V component, vertical component is there. So V velocity at N will be V velocity at capital N, V velocity at capital P, and divided by 2, like that. So you see UW, UN, and US are calculated in that manner. And once we know that UF and all UE values, which is nothing but also FE, okay, F values, FF values. Now we can say generally this is FF. We can say it like FF. F can be your east face, your west face, north face, and south face. So FF means you can say FE, you can say FW. So we'll just generalize it. So in general concept, then if the value of FF is greater than 0, then we'll say that whatever phi f is nothing but equals to phi p. Else it is phi f capital FF. So small f, capital F is nothing but capital E, capital W, capital N, capital S, capital T. So for example, in this case, suppose you are talking about east face, and we observe that suppose FF means FE. FE is greater than equals to 0, then we have to take FE is equals to FP, capital P. Otherwise, if that is not the condition, then phi E will be equals to phi. What is FF? FF is for east face, it is east east. Okay, so phi e will be there if the condition is not satisfied. Similarly, you will keep on doing for other faces like west face. You will keep on doing for the north face. You will keep on doing for the south face. This is a generalized equation for that, and this is called as upwinding scheme. Okay, this is the one scheme I have discussed. There can be second order upwind, there can be quick scheme, and you can, I will just give you the reference. You can go through this reference for these higher schemes, but I just wanted to make a point how these terms are discretized and solved. Now comes to diffusion term. Now this diffusion term are also like surface integrals. So surface integrals, what are the surface? East surface, west surface, north surface, south surface. Everywhere we are doing this discretization, integration. Now here we write this gradient of phi east, then delta s east. We just simplify them, we then note them like this, and now here we know that this delta s, already know that it is delta y. This surface vector is nothing but delta y delta x, like that, with negative signs. So negative signs are incorporated here in order to change this. This could be phi p minus phi w minus delta y. So they are brought in. Now here, in order to get gradient of phi, now gradient of phi, suppose gradient of phi del x, then it is obtained del phi del x is at any p. So del phi del x at p is calculated as the phi east forward, phi east central difference, phi e minus phi p divided by whatever delta x present in that. So central difference is used. Central difference is used in order to get the value of gradient at p. So at here we have east cell center, here you have the west cell center. To get the gradient at this pith center is our focus current location. So at this current location, what is the gradient? To get that gradient, we use central difference. So whatever distance delta x is there in the x direction, now see we are in x direction. So the distance between that and divided by this is giving you the value of the gradient of phi. So in general, we can write FFD phi as alpha grade phi f and SF dot SF vector. Okay, so we can define like this. Okay, just to note them. So finally, our discretized forms in general, they become like this. Okay, volume at the pith cell phi p n plus 1 minus phi p n delta t, and you have summation of phi a and f's, that is from your convection term we already seen. We have summation of all ff d phi m d phi terms, and here the n plus 1 and n terms are given, and there are m, there is m and m given. Now based on the nature of the problem, it can be explicit, it can be implicit. If m, all m are n plus 1, then it is implicit. What does it mean? It means that only there are more than two unknowns. If there are more than one unknowns are there, then it is called as implicit. Okay, and in explicit cases, we have only one unknown and all other knowns. So if you replace m by n, n means old values, known values, that is old values, and this is unknown means new values. So to get the new values, we will have all known values. In that case, we say that it is an explicit scheme. Otherwise, if you have more than one unknown, if m is replaced by n plus 1, m is replaced by n plus 1, then this becomes implicit. What does it mean by explicit and implicit? Explicit is there, then you can directly calculate the value of phi p, but when it is implicit, it means that we have to solve these equations. These may be many equations. Okay, so these equations you have to solve simultaneously. We have to solve for every point that grid points, we have to solve simultaneously. So we have to do some sort of iterative method and things like that. So that is the meaning of implicit. In explicit, we do not need to solve simultaneously these equations, and we can directly get the answer. But explicit have a delta t limitation, stability problem, and implicit schemes do not have stability problems. So delta t restrictions like Courant number, these do not come into picture, which comes for explicit schemes. So implicit schemes are mostly used in CFD. Okay, now with this, how to get it for discretization for irrespective of staggered grid and collocated grid. If you imply staggered grid and collocated grid schemes, you will get little modifications and you can get those. And how do you apply boundary conditions? For example, this is a domain. Okay, this inner is a domain. So this is your computational domain, and now boundary conditions are given. So suppose at this boundary, this left boundary condition is given. Now this boundary condition can be of Neumann type or Dirichlet type or Robin or mixed type. Okay, now I'm only discussing Neumann boundary condition and Dirichlet boundary condition. So suppose a Neumann boundary condition is there, it means that del phi del y is equals to q naught. This is the condition given over here. Then here what will say that this is interior point int and this is a fictitious point. So to apply boundary condition, we have to consider a layer of fictitious cells around the boundary. Okay, so these are all fictitious cells. So that is one important thing you have to remember. Whenever you want to apply boundary condition, you have to consider a layer of fictitious cells. And once you use fictitious cells, so whatever the value here, you will say fictitious. So phi interior, so what do? You take phi interior minus phi fict delta y is equals to q naught. This will give us the value of phi fict like this. And suppose the homogeneous condition is there, so you have to just simply say equals to 0. So phi fict will be equals to phi int because q naught is 0. So phi fict will become phi int at n plus 1. Remember this n plus 1. Always boundary conditions are given at n plus 1. They will never be nth level values. They will be always n plus 1 value. But once you solve for interior domain, these boundary conditions always has to apply after solving interior domain. So once we solve for all these points, once we solve for all these interior points, then only boundary conditions are implemented. Okay, you don't have to implement boundary condition before that, because if they are always n plus 1. So once they are calculated here, n plus 1 phi interior, this is known even though it is n1 plus, because from interior this solution is known now because you have calculated just now. So these are known for this thing. In case of Dirichlet boundary conditions, so always it is a sort of some phi is specified phi q naught. So what do you do is you take average, whatever interior is there, whatever fictitious is there, that average is calculated and you will get q naught is a known value. This is a known value, so it doesn't matter whether it is n plus 1 or 1, and these values are calculated like that. So boundary condition implementation is done through the fictitious cell. Okay, that is a point. And how it is done, I just shown with examples. So if you do this, you can you can get but we were discussing about the convective diffusion equation. Now if you take a momentum this Navier-Stokes equation, then you get a pressure terms like del p del x 1 by rho del p del x. Now how do we do that, these terms? So we again take a triple integral of that, volume integral of that term. So we define something like p q vector, which is p I kappa I cap. Then we can write these integrals as like this. Okay, and using Gauss divergence theorem, we can convert volume integral into the surface integral. So finally we can write surface integral like this, and after simplification we can get equation like this. So in case of finite volume u momentum equation, we get this pressure as a source term. In v momentum equation, y momentum equation, we get pressure as this source term like this and like this. Now we can integrate these equations in the similar manner we did for east face, west face, south face, north face, top and bottom, if it is a 3D. So you can do these integrations for those cases and get those values, proper values. So once you get this, your Navier-Stokes equations will also the discretized forms will look like this. So with this discretization, you can have, and this m can be replaced by n plus 1 or n will decide whether it's implicit or explicit. But pressure, when you are solving Navier-Stokes equations, pressure is always unknown, because for incompressible flow, unknown for incompressible flow, because in continuity equation there is no pressure term, there is no density term, so there is no way to calculate pressure. So pressure is always unknown in this Navier-Stokes equation, and the that lead to the what is called as you have to find out the pressure correction equation, Poisson equation for pressure correction, or pressure equation for collocated grid, pressure correction equation for staggered grid, and you have to solve these three equations. So once you solve these three equations, you get the solutions. Okay, that is called. I mean, you get the solution in that sense. Okay, and
Sorry to interrupt, sir,
you
but
you
we are
you
running
have
out
this
of
pressure
time.
velocity decoupling, that you can remove that decoupling by staggered grid. In case of collocated grid, that pressure velocity pressure velocity decoupling is done to something called as some fix called as momentum interpolation, and it doesn't show any problem with that. So all the, what does it mean? That I mean, you have suppose these cells, then your interior cells should depend upon the so velocity at this point only depend upon the outside pressure. So that is a scene is a problem. So velocities at this point should be connected with the pressure at this point, that this cell along with the neighbor cell. So then that situation is a coupled. Otherwise, if they are not in relationship with each other, then they are decoupled with each other. So that is done through this staggering or collocated stagger grid mostly. That decoupling is maintained with this, but stagger grids are very complicated for complicated problems. And collocated grids are mostly favored in the CFD solutions. So if you solve this, the your simple algorithm will look like this. You have to solve the momentum equation separately for each
Hello, sir.
phases.
Am I audible?
Yeah, I
Actually, sir,
think
we are
I'm.
running out of time, sir.
Yeah. So how much time should I finish now, or
If you have any concluding remarks, you can make that, sir. No issue.
okay? So I'll just take maybe just 5 to 10 minutes,
No
and
issue.
I'll just bring into that. Okay, so here you can solve the momentum equations with updated values of pressure and mass flux, and then you can solve for pressure correction equation. So once you solve pressure correction equation with this momentum equation values, then you can recently obtained velocity field values, then correct the mass fluxes, pressure and velocities in pressure correction equation, solve the other equations. I mean, for scalars like any other scalar like temperature or species mass fraction, or turbulent and quantities like k, epsilon, and other terms. Okay, and you can check for the convergence and continue when you continue till you get the convergence. Now when you consider the spray scenario, you can model, as I said, Euler Lagrangian and Euler and Euler Lagrangian, and you can model turbulence by Rans model or LES or DNS. LES and DNS can be accessed from these very good books, and Rans is generally used for your, still it is used for your practical applications, and they are reasonably okay to go ahead with. Now in this scenario, there are many intermediate steps happen before formation of drops, that can be modeled using these models available in literature. And if you consider this spray scenario, we have these basically two types of model: kinematic model and hydrodynamic. Kinematic models, essentially they consider the molecular dynamics, and hydrodynamics model do not consider the molecular nature which is happening of the is the extinction. So what happens is the droplet is there, when it evaporates it's like itching, it is taking the material from it. So that is modeled in dynamics model. Hydraulic model do not consider that thing. and hydrodynamic models can have, suppose we have this droplet phase, then this is a liquid phase, and there will be a gaseous phase. So there are certain models for this, there are certain model for this. So you have two separate models for that kind of scenarios. So single droplet liquid phase, you have constant droplet temperature models, infinite liquid models, spherical symmetry models. So what does it mean? That inside a droplet you can assume that the temperature is constant over a space and time. In second scenario, you can consider that temperature is varying with respect to space and time. And not only that, there is a recirculation inside the droplet. Okay, so three scenarios can be considered. And there can be other models like vortex. So stream function vorticity models can be used to model that. You can use Navier-Stokes equations. These two models are very complicated, time consuming, so still 2 to 4 models are used in CFD. In case of gas phase model, we use mostly classical model, which says that in the droplet and near the droplet there is a saturation of the vapor. Saturation of the vapor is the meaning of the saturation of vapor is that whatever the diffusion, fuel diffusion rate is there, that is nothing but the evaporation rate of the fuel. So there are other models of Ambrosion, Sirignano, Abeck, and non-equilibrium model, which correct the situation. In case of Abraham-Jones-Sirignano, they consider over the droplet very near that you have boundary layer effect, so that boundary layer effects are considered. Au and Abel not only consider boundary layer effect, they consider thermal effect, thermal boundary layer, as well as mass boundary layer. And just a modification of Abraham-Jones model is a Au model. Non-equilibrium cases, they do not consider equilibrium near the phase. So here there is a equilibrium considered. In case of classical model, non-classical model do not consider non-equilibrium, and they use the kinematic models like Langmuir more kind of models. And in classical models, we can calculate the species mass fraction using Clapeyron equations, Clausius-Clapeyron equations type. So that is not possible with non-equilibrium model. And once you do the modeling, there are relationships in terms of dm dt, dt by dt. And in most of these case, correlations are obtained. Nusselt number as a function of Reynolds number and Prandtl, Sherwood number as a function of Reynolds number and Schmidt number, to incorporate the convection. Suppose you have a droplet and then you have a convection here or conduction, and these effects are there. These are modeled through this empirical correlation. So in this scenario, you may get these equations: continuity of mass, momentum, energy, and species mass fraction. And in these cases, you get in energy, you get sensible heating of droplet, latent heat of droplet. So these source terms will come into picture, and you will be able to solve these equations. Okay. So these equations, dm for mass of particle, velocity of particle, as you said, this is a Lagrangian kind of forms. You get the source terms here. Okay. And here bm is a Spalding mass transfer number, where yf is a ratio of y. So y is Clausius-Clapeyron equation. CD and the SHFB, I mean the Sherwood number and Nusselt number are used to know the value of Kc. And AC, K is thermal conductivity, H is heat transfer coefficient. These correlations are used in order to get the values of these Kc and H. Okay, so once you solve this problem on any domain, so this is a 1D domain we have considered. So in a 1D case, there is a drop coming, and then this drop is evaporating in the x direction. So in order to model 1D case in a 2D framework, we have done, and we have used use a symmetry boundary condition here. Symmetry boundary condition, it means that nothing is happening in this direction, only happening in is one direction. So using this and boundary conditions mentioned here, various boundary conditions you can note, and we got the grid independence first, and the result shows the mass fraction of ethanol with the analytical solutions. The fluent is a red one, and there are certain models we have developed in our case. which are C1, C2. I have not discussed these models, but these models are compared and found to be that C5 model is close to the analytical results. Again, droplet diameter, that droplet is reducing in its diameter, so prediction of that droplet with time is plotted, compared with the fluent solution, analytical solution. Our models, C5 model, again gives very good results. Okay, so what is I'm saying is that multiphase flow is very complex. Empirical correlation pressure laws are not universal, so CFD is necessary, and you have to use a continuum framework, and these equations are still under research, and to find the closer models, and you can always go for finding closer model for evaporation, for example. So the one model which I have discussed for evaporation model is that single droplet model. Even though in many in the real cases there are many droplets in spray, what is done is a single droplet modeling is done, and what a single droplet modeling is there, then it applies to many droplets, and that is what the state of art is. So that is what I mean to say here. And most of the CFD software still uses classical model, and you can always propose many other models or classical models, and you can carry forward your research in that direction in order to predict the operation rate accurately. Thank you for your time. Any questions you have, please?
Thank you very much, sir. It was really a nice session. Any participant having any questions, they can ask. Yes, any participant having questions? I just want to ask you, sir, one thing, that you
Yeah,
have
please.
explained simple algorithm. So,
Yeah.
any other CFD technique which is popularly used for this multi-phase flow, like pressure correction method and
In
any
terms
other?
of see, if you are asking me about the finite, I mean this CFD method, then there are many other CFD methods like lattice Boltzmann method, that is also popular. Now you are asking about this pressure velocity and this effect. Okay, so this pressure velocity coupling is, as I said, about this staggered grid and collocated grid. Okay, so staggered grids are mostly favored because in staggered grids it is found that the velocities and pressures are not decoupled, so you get a good coupling, and you do not get any problem in getting solutions. But that was in the same time collocated grids were there, and if people are using the same strategy in collocated grids, they used to find that the problem is there in terms of pressure velocity decoupling. To fix that, they use a that is something I said, that fix is called as momentum interpolation. Okay, so if you do that momentum interpolation, you do not get the pressure velocity decoupling. And you can, and right now in present day scenario, even Fluent and all this everywhere, in all CFD codes, this collocated grid arrangement is used. The difference between collocated grid and staggered grid is known to you, and
Yes.
I think many our participants. The all the flow variables in case of collocated grid are calculated at the cell center, and in case of staggered grid, only pressure is at cell center, but the velocities are always calculated at their respective phase centers.
Okay. Okay. Thank you. Thank you very much, sir.
Yeah, welcome.
Okay, so on behalf of Mechanical Engineering Department, ADIT, I thank you very much, sir, for accepting the invitation and delivering such a wonderful talk regarding
It's my
CFD
pleasure.
analysis of multi-phase flows. You have covered it very nicely, sir. You have explained that FEM, which is a really important discretization techniques, nicely, and the other fundamentals related with multi-phase flow, such as their applications of multi-phase flow, the fundamental governing equations in this particular domain. So thank you very much, sir, for sparing your valuable time. Thank you.
It's my pleasure.
Thank you.
Yeah, yeah. See you next time also.
Sure, sure,
Uh,
sure.
Thank you, Maharshi.
Thank you. Thank you very much, sir.
See you. Bye bye.